We're going to continue justifying the shapes of atomic orbitals using quantum mechanics, but we're now going to approach it with angular momentum as well as just the sine and cosine waves showing us the shape of orbitals in 2 dimensions. So this will actually allow us to justify why there are more orbitals than just 3 in the x, y, and z direction as you increase to the d orbitals and the f orbitals. So we're going to recap what angular momentum is and then how that relates to wave functions. And then we're going to apply that to the shapes of the orbitals and add in a little bit of a complicated thing that may undermine what you think atomic orbitals actually are. So let's recap. Angular momentum. So from spectroscopy, we should know that there are 2 completely equivalent ways of defining angular momentum. We just distribute the variables slightly into different symbols. One, we treat it as the product of the moment of inertia and the angular frequency. Secondly, we could define it as a radius of a rotation and its linear momentum, and that's done as a cross product. So that produces a vector quantity. So just like momentum, linear momentum has a vector, it has a magnitude and a direction. Angular momentum also has a magnitude and direction. And there is an interesting consequence of defining it as a cross product and a few other things about angular momentum, in that if we have a particle making an orbit and this is the radius sticking out from the center and this is its linear momentum going forward in a particular direction, and then if the angular momentum is this cross product, it follows something called a right hand rule, which means you take a right hand, you curve the fingers around in the direction of the rotation, and angular momentum sticks out in the direction of your thumb. It's completely perpendicular to the plane of rotation, which is worth reminding yourself of because it is quite counterintuitive. Why would the vector for momentum stick out in a completely different direction to the actual motion? It's a very odd fact. Nevertheless, it is justifiable because we can detect this. If you have a particle that's charged, an electron for instance, and you set it moving, well, that rotating charge produces a magnetic field in the direction of the angular momentum. So we can detect angular momentum as a magnetic field. And that is going to be really important when we move on to spin and magnetic resonance, because these orbiting or rotating or spinning particles have magnetic fields associated with their momentum. So let's jump back to the wave functions for a moment. So these are the wave functions that generate from particle. If it's on a ring, we confine a particle to a ring, it generates these wave functions going from 0 degrees to 360 degrees. And what you can see is that energy should increase as we increase the momentum from 0 to 1 to 2 to 3. The wavelength is shortening, therefore the energy is increasing. So here we have the highest kinetic energy in an angular direction. Here we actually have no kinetic energy orientated in an angular fashion. That would be true for an s orbital, for instance. There is no angular component to that orbital. Then we go to p, d, f. The number of nodes distributed angularly increases, the amount of kinetic energy increases as well. That also means the angular momentum must also increase, and that the angular momentum is quantized. We only have a set amount of angular momentum. An electron can't take any value. It must be constrained by the fact that it's orbiting to any of these values, so its angular momentum is also quantized. So we can detect angular momentum through a magnetic field, really important for when we get onto NMR. The electrons generate that magnetic field, as do protons, and that angular momentum does come from both orbit and spin, although for now we're mostly concerned with orbiting. If you've done atomic spectroscopy, you will come across spin-orbit coupling, where we begin to include both together for a short recap of that. Orbit is usually given the L number, spin is usually given S, and we add those together, we usually give it J. Hence why rotational spectroscopy also uses J as its rotational quantum number. The nomenclature and the choice of symbols are quite related like that. So let's look at the angular wave functions again. We know going from 0 to 360 degrees, with this where L equals 1, well, we go from positive to negative, and therefore it must go from positive to negative as we spin around. That justifies the shape of these orbitals, at least in 2 dimensions. Let's look at this from a slightly different angle. Previously, we talked a bit about there is an interpretation here where we say one orbital is the electron orbiting clockwise and the other one is anti-clockwise. So we now know the direction of rotation. Let's apply the right-hand rule to this. If this is spinning in this direction, the right-hand rule says that it should be, here's the thumb pointing out here, the angular momentum must point in that direction. If it spins in the opposite direction, the angular momentum must be in the other direction, down here. So the angular momentum is quantized. It is a fixed value, but it points in different directions for these orbitals. Now, if an alarm bell is kind of ringing in your head saying that this doesn't make sense, because, well, one's orientated X, the other's orientated Y, why would the angular momentum invert? We could rotate this diagram just 90 degrees and the angular momentum wouldn't flip. So if that's worrying you, don't worry, we will scratch that itch in a moment, especially anyone who might have done a lot of physics before. The way chemists approach this is looking at these orbitals may not necessarily make sense to a physicist. We are going to cover that at the end. It'll add a little bit more of a complexity to it that chemists aren't used to, but, well, it's good to have a little bit of complexity and simplicity at the same time. Let's just rotate one of those up on its edge for a moment. And here we get the PZ orbital. If we follow the right-hand rule here, we know that the angular momentum here must be pointing out in this direction. Or is it? It can actually point in any direction at all in the XY plane. All we know is that it isn't quantized anywhere in the Z direction. It is entirely in the XY plane, although in any direction. We don't know which direction it is. That is a consequence of quantum mechanics. We know that some things are quantized in one direction, and we know that really well. We then lose the information in the other directions. So while we know that that L must be orientated down level on the XY plane, we don't know whether it's pointing in the X direction or the Y direction. So we can actually begin to plot these on a graph, and you'll probably see these diagrams more often than you'll see them associated with the orbitals. Drawing them on top of the orbitals is just to kind of help make that connection. So if we have an angular momentum entirely orientated in this direction, well, its length is 1, quantum number L is 1. Its quantity in the Z direction is 0, and that is what ML equals 0 means. We can then begin to point that up. It's the same length, L is equal to 1, but ML is equal to plus 1. It is plus 1 in the Z direction. And the opposite to that, again, L is still equal 1. The magnitude and size of that vector is the same. The angular momentum is quantized, but its direction is the opposite. ML is equal to minus 1. And you usually see diagrams like this. And sometimes these are put at an angle rather than pointing directly up, because we actually don't know how that's orientated in the XY direction. There is still some uncertainty there. So some diagrams even depict them as cones. We know that it's quantized in the Z direction, but we lose a bit of the XY, that lateral information. We don't know where it is. So we know that this has a lot of uncertainty associated with it. So we sometimes draw them as cones. Sometimes the diagrams just have these directions and imply the uncertainty. Sometimes we draw cones of uncertainty around them. So if you see how the diagram, that's why that is. We still have a bit of uncertainty. So let's escalate this up to L equals 2, the d orbitals. Again, we go from positive to negative to positive to negative. So positive, negative, negative, around 360. And that's the typical shape of a d orbital. We can do the exact same thing again. One of these is circling clockwise, the other is counterclockwise. Let's apply the right-hand rule. So this one must have its angular momentum pointing up. This one must have its angular momentum pointing down. So L is equal to 2 here, L is equal to 2, but in opposite directions. When I'm drawing them on here, I'm kind of hand waving away that uncertainty, but when we talk about pure angular momentum, we do have it. Now let's tip one of these on its side, and we get that classic dz squared orbital. It looks a little bit different. It's got this completely symmetrical ring around it, but that is a consequence of us losing that xy information. Let's apply the right-hand rule to this. L equals 2, the angular momentum must be out on the xy plane, but it could be in any direction. It could point out here, it could point out here, it can point out here. All we know is that it's not orientated in the z direction at all. And that's why the dz squared orbital looks a little bit different. If you cut a cross section through it, you end up with that normal looking d orbital shape here. That's a cross section through. But if you took a cross section through another way, you get the exact same shape. Effectively, this is a combination of one orbital that looks like this in that direction and another orbital that looks like this pointing out 90 degrees to it. We add those both together, we get this nice cylindrically symmetrical donut in the middle. It's a really nice orbital to look at, really interesting if you want to plot it on a 3D calculator as well. But that's not the only d orbital we have 5 of them. So we have one where the angular momentum is pointing up, one where the angular momentum is pointing down, one where it's pointing completely in the xy direction, no z at all, and these two others, the dzx and the dzy or yz and xz, I can't remember which way around it goes, it doesn't matter. These, the angular momentum is only halfway up. We have a particular quantization in the z direction and in the xy plane as well associated with that. And that kind of makes sense for those orbitals. If you have a look going around it, it still looks like it changes phase. If you go round kind of polar wise, it also changes its phase. So there's definitely energy quantized in both directions there. So when we come to plotting out ML for this, L is equal to 2. We have an L equals 2 pointing that way. That's ML equals 0. We have an L equals 2 pointing that way. That's ML equals plus 2. ML is equal to minus 2. And then 1's in the middle where ML is equal to plus 1. And ML is equal to minus 1. We've quantized different amounts of that L equals 2 in the z direction. Either all of it in the z direction, or only half of it in the z direction, or none of it in the z direction. So that's how quantum mechanics is actually quantizing the angular momentum here. It's not necessarily generating those orbital shapes as we're about to see. It's quantizing angular momentum in different orientations. So let's scratch that whole itch. The reason that those angular momentums don't necessarily match up with the orbitals, and why there is one pointing up and one pointing down, even though the orbitals just twist 90 degrees, comes from the fact that those orbitals that we draw and that we're taught to draw from the first year of chemistry aren't real. Well, they're real in a mathematical sense, as in not complex. They don't have that imaginary unit in them. And that's pretty good for us as chemists, because you can't really draw or visualize orbitals if they have complex numbers in them. You sort of end up with an orbital that might look like that, and then sort of another orbital that's got a positive and negative, but in the complex plane aligned with it, it's quite difficult to draw and visualize. So what we end up doing is taking linear superpositions of those, and we end up with the real orbitals that we've been drawing for the last couple of years. So the orbitals we draw are not the direct result of those quantum numbers. The quantum numbers go into other orbitals. So let's show those superpositions. We actually have 3 orbitals. We label those with the value of ml. So P means that L is equal to 1. 0 here is the ml value. And just so happens when that's 0, we get the PZ orbital. We don't need to do anything fancy with it. It's exactly the same. But P1 and P minus 1 here, where ml is equal to plus or minus 1, those are complex orbitals. They have that I is equal to square root of minus 1 in it. But if we take these superpositions, which we've seen before, we add 2 functions together, or we subtract 2 functions, and then we normalize it with that 1 over square root 2, we get a new orbital. And these happen to be easy to draw, z, x, and y. It doesn't need to be 1 over square root 2. You can see from the animation there, we can actually vary that and mix in different quantities. So we can go entirely from a complex orbital to an entirely real orbital. And you can see that there's a 3D plot of that that's actually quite complicated to read when it's in its imaginary complex form. You have to learn how to read colors that map to the imaginary plane, and it takes a while to get your head around. But you can see this kind of clean donut shape that makes a bit more sense than our dumbbell shape that we might be used to. It's kind of clearer that there is a continuous orbit around there, even though it is still quantized. So we kind of ignore the complex numbers, we take these superpositions, and then we plot out as x, y, and z. So P1 and P minus 1, or P plus 1 and P minus 1, those orbitals are the ones that have angular momentum associated with them. Right, so let's just summarize the whole of angular momentum again. So angular momentum here is quantized. That's our L value. It can be equal to 0, 1, 2, anywhere up to n minus 1. It's always related to the principal quantum number. And the direction of the angular momentum is also quantized. So n, the principal quantum number, tells us how much energy we've got. L tells us how much of that energy is distributed into an orbital angular fashion. ml tells us how much it's pointing in the z direction. And ml therefore roughly controls the orientation of the orbitals. The shapes of the orbitals that we're used to seeing all have angular momentums that are pointing in different directions, or at least they're superpositions of orbitals with angular momentums pointing out in different directions. They're still useful from an electron density point of view, but they don't quite map on perfectly to this angular momentum idea. If you can follow that, great, but it's not essential from a chemistry perspective to be talking about the complex orbitals. We still get a lot of use out of the real orbitals, and they've got a very strong amount of predictive power, even when they're not technically right.